All right, here's our topic, delta G and K. K for equilibrium constant. We want to relate them. How does one tell you this other? Just like how does a shooting percentage tell you how much playing time? So if I know the K, what's my delta G going to be? A comparison could be, and this is the transitive property. If these two are equal to C, then what does that mean? They're both equal to each other. So that's the transitive property. It's kind of, that's what we're going to do, but we're going to relate delta G and K. All right, so quickly review, equilibrium constant K is a pseudo constant, meaning because it's not really one value. There's lots of values that's dependent on temperature, but we still call it the equilibrium constant. It's on your reference sheet. There's tons of different formulas, but in general, they all mean products over reactants, their concentrations, their pressures. And knowing it tells you something about the reaction. It's big, product favor if it's small, other way. Delta G, Gibbs free energy, is also on your reference sheet. It has to do with thermodynamics, comparing like the energy before and after and entropy. And there are two different formulas. The formula, here's one of them, and depends on enthalpy and entropy and temperature. This tells you whether or not reaction is spontaneous, whether it's thermodynamically favorable. I've used the term, does the universe want it to happen, or that expression. All right. Now, I want to sort of relate a big idea with these numbers. This image comes as the cosmos. It's from the NASA website. You can use web images from NASA, provided you let people know it's from NASA. This is from the Cosmos field, which is short for Cosmos Evolutionary Survey. It's 12 billion light years old. So we're seeing light that was made 12 billion years ago. And the tiniest dots are galaxies. So there's a ton of galaxies here. My three companions, they go stargazing and they ponder big, deep questions. That's what I used to do or what I do when I go stargazing. But anyways, this is an idea that the universe knows itself through numbers. Like, numbers are a language that you can use to understand what's going on in the universe. I got this idea from a gentleman who I can't remember his name, but it was in a course. It's not my idea, but I thought that was really cool. The same thing goes for chemical reactions. It's kind of an odd concept, so let's ask the cosmos for a little bit of explanation. One such example is Einstein's famous equation where E equals mc squared, where this idea that you can relate them to can be captured. Relate matter and energy is captured in this equation. Now, that doesn't tell us everything we need to know about energy and matter, but it's one. It's like a piece of the puzzle. And chemical reactions, they have the same similar numbers. K tells us a lot. This equilibrium constant, all right, tells us a lot about reactions. Now, here's how they're connected, the meat and the potatoes of the video. I've got these two numerical values about a reaction, the equilibrium constant and the Gibbs free energy. They're both related, they're both predictors, and they both can predict in a way what the cosmos is tending to do with the reaction, and you can use them to predict the other value. And by that, I mean, if you know K, you should be able to know what delta G is. If you have an equilibrium constant that's greater than 1, your Gibbs free energy is going to be negative, and the universe is saying it's favoring the products. And it's the opposite. If your equilibrium constant is 1, this is very rare, your delta G would be 0, and the feeling of the universe is like it doesn't favor either reaction. Let's look at some examples. Here's one such example, this reaction of hydrogen gas and iodine gas to make hydrodoic acid. Yeah, that's right. And here's my delta G. It's negative. My K should be greater than 1. There it is. Here's another reaction. This is hydrochloric acid as a gas. Notice my delta G is a lot more negative, bigger. So my K value should also be larger. Look at it. That's just like, where do they come up with that number? It's so big. It's so cool. So once again, negative delta G, K is greater than 1. One more example. This is the turning of nitrogen oxygen gas to mononitrogen monoxide. It probably has a specific name that I can't remember. Here we've got a really small K, all right? It's a small decimal. That means our delta G should be positive, and indeed it is. I'll be darned. Now this means is this reaction doesn't want to happen. It's going to favor your your reactants. And yeah, here are my sources. Gibbs Free Energy is the best, and that image came from NASA, and thank you so much. All right, have a good day.